We have photographed galaxies 13 billion light-years away. We have mapped the ocean floors of Europa in our minds before any probe has touched them. We have detected the ripple in space-time from two black holes colliding a billion years ago. And yet, if you ask what exists directly above and below our own sun, the honest answer in 2025 is that we barely know. Not because the technology doesn't exist. Not because no one has thought about it, but because the universe placed some of its most extraordinary secrets in the one direction we have almost never looked. What lives up there is stranger, wilder, and more consequential than most people realize. And the reason we haven't seen it is one of the most counterintuitive facts in all of planetary science. Start with something you have probably never thought about. The solar system is flat. Not roughly flat, not approximately flat, but astonishingly, almost embarrassingly flat. If you built a scale model of the solar system the size of a football field, every planet, every asteroid belt, every comet in the Kuiper belt, the entire visible machinery of our cosmic neighborhood would sit inside a disk less than a millimeter thick. The whole thing. Neptune is billions of miles from the Sun, but it orbits almost exactly in the same plane as Mercury. Jupiter and Saturn, despite their enormous size, barely deviate. Even the asteroid belt that sits between Mars and Jupiter hugs the same flat ring with extraordinary discipline. The solar system is not a sphere. It is a razor. And directly above and below that razor, rising out of the flat plane in both directions simultaneously, lies a realm that is almost entirely unexplored. Not metaphorically, literally. No spacecraft has ever reached the solar poles from a clean vertical angle with modern instruments. No high-resolution image exists of the Sun's North Pole taken from directly above it. The polar regions of our star are, at this moment, among the least photographed surfaces in the entire solar system. We have better images of Pluto's surface, taken from a spacecraft that traveled 3.5 billion miles, than we have of the top of the star sitting 8 light-minutes away. The reason the plane exists in the first place comes from physics that is over 4.5 billion years old. The solar system was born from a rotating cloud of gas and dust. As that cloud collapsed under its own gravity, the way spinning objects always do, it flattened. Conservation of angular momentum forced everything rotating in the same rough direction to settle into a shared disk. The planets formed within that disk. And so everything we have ever built, launched, or sent into space has also been born inside that same flat structure, moving sideways through it at tremendous speed. Earth circles the Sun at roughly 30 kilometers per second. Every spacecraft we have ever launched inherits that motion. Going sideways is easy. It costs almost nothing extra. But climbing out of the plane, perpendicular to everything, means first canceling that enormous sideways inheritance. And that is where the energy requirements become almost hostile. To go straight up out of the ecliptic plane, a spacecraft would need to shed roughly 30 kilometers per second of orbital momentum before it could even begin climbing. For comparison, reaching Mars requires about 4 kilometers per second of delta V. Going to Pluto requires less total energy than going straight up. This is the single most counterintuitive fact in solar system exploration. The closest direction, directly above the nearest star, is also the most energy-expensive direction we have ever tried to reach. It is not a question of telescope power or computational limits. It is a question of basic orbital physics, and the physics has been merciless. Which means what lies above and below the Sun has remained largely hidden. And what is hidden there turns out to be shaping everything we experience. The poles of the Sun are not quiet. They are not calm, featureless caps on a rotating sphere. They are the origin point of the fastest, most powerful streams of solar wind in the entire solar system. A feature called a polar coronal hole opens at the solar poles like a valve in a pressure system, releasing streams of charged particles at speeds between 700 and 800 kilometers per second. These are not the slow, turbulent gusts we detect in the equatorial plane. This is a clean, fast, relentless current of plasma roaring outward along magnetic field lines that have broken free of the sun's tangled magnetic equator. The fast solar wind from the poles is one of the fundamental drivers of space weather throughout the heliosphere. It shapes the radiation environment around every planet. It affects satellite electronics, astronaut safety, communications infrastructure, and the aurora we see glowing at high latitudes on Earth. And for most of history, we have been measuring it sideways, from the edge of the plane, rather than from above, where its full structure is actually visible. The magnetic field story is even more dramatic. The sun's magnetic field reverses polarity completely every 11 years, in sync with the solar activity cycle. The process begins at the poles. Magnetic field lines rise from deep within the solar interior and emerge at the surface, migrate toward the poles over years, and eventually cancel out the existing polar field before rebuilding it with opposite polarity. This is the engine that drives the entire 11-year solar cycle, the same cycle that produces solar flares, coronal mass ejections, and the storms that can knock out power grids on Earth. The poles are not a quiet corner of the sun. They are the control room. And we have only just begun to look inside. The first mission that ever gave us any real information from above the solar plane was Ulysses, launched in 1990. It could not go straight up. Instead, it traveled outward to Jupiter first, using the gas giant's gravity to bend its trajectory nearly 80 degrees out of the ecliptic in a maneuver that took years to execute. From that tilted orbit, Ulysses fell back toward the sun and made the first direct in situ measurements of the fast polar solar wind. The mission worked. It was one of the most elegant gravity assist trajectories ever designed. But Ulysses carried 1980s instruments. It had no cameras capable of imaging the polar surface. We felt the wind from the poles without ever seeing its source. The second mission is still running. Solar Orbiter, launched by the European Space Agency in February 2020, has been using repeated Venus gravity assists to tilt its orbit progressively higher. In March 2025, Solar Orbiter captured the first direct images of the Sun's south pole ever taken in human history. Not artists' impressions, not models, actual photographs from an angle no instrument had ever reached. What they showed was extraordinary. A magnetically chaotic, structurally complex region unlike anything visible from the equatorial plane. Twisted field lines, bright plumes, dark cavities, a surface that looks completely different from the sun we know, because it is completely different. The poles of our sun are a foreign landscape, and we have only just seen the edge of one of them. But the sun is only half the story of what lives above and below the plane. Because the space that extends outward from the poles, rising away from the solar system into the vertical dimension, is itself an environment unlike anything in the planetary disk. The ecliptic plane is dusty, 4.5 billion years of cometary debris, asteroid collisions, and the slow disintegration of small bodies has left a thin but real haze of dust particles scattered through the plane of the planets. This dust is not invisible. On a dark night, away from city lights, just after sunset or before sunrise, you can see a faint pyramid of light rising from the horizon called the zodiacal light. That glow is sunlight scattering off the billions of particles suspended in the plane you are living inside. It is the lit interior of your own solar system, visible to the naked eye. A spacecraft climbing directly above the ecliptic would rise out of that dust layer within months. The environment above and below the plane is dramatically cleaner, darker, and quieter than anything inside the disk. Less scattered light, less background interference, For a telescope trying to detect the faint signal of a potentially habitable planet around a distant star, or trying to resolve the structure of a galaxy far beyond our own, the vertical regions above the solar system would be among the best possible observing positions in the entire solar neighborhood. The noise that surrounds us inside the plane simply doesn't follow you up. And then there is the heliosphere. The vast magnetic bubble generated by the solar wind extends outward from the sun in all directions, eventually pressing against the interstellar medium at a boundary called the heliopause. Inside this bubble, the solar wind dominates. Outside, the galactic environment begins. Cosmic rays that would otherwise bombard the inner solar system are deflected and slowed by the heliosphere. It is, in a meaningful sense, the shield of our solar system. And we do not actually know what shape it is. For decades, the assumption was that it looks like a comet, a rounded nose pointing toward the direction of our galactic motion, and a long tail streaming behind it, billions of miles into the interstellar medium. The image appeared in textbooks. It was treated as settled. Then, in 2020, a team at Boston University led by astrophysicist Merav Ofer published a different conclusion. Using updated models built on NASA Voyager data and observations from the IBEX spacecraft, they found the heliosphere is probably not comet-shaped at all. The new model resembles something closer to a deflated croissant. Two jets curling back from a central bulge, with no significant long tail. The shape is driven not just by the solar wind pressure, but by the internal behavior of the magnetic field, which channels plasma into the jets rather than allowing it to spread into a smooth tail. The reason we cannot confirm which model is correct is, once again, geometry. The Voyager spacecraft crossed the heliopause moving almost entirely within the plane of the planets. We got data from 2 points, both near the equatorial region of the bubble. To see the actual shape of our heliosphere, you would need measurements from above and below it. You would need a probe climbing out of the plane and looking back inward from a high angle. That vantage has never existed. We live inside a bubble whose form we still cannot agree on, because we have never sent anything far enough above it to take its picture. What this means, taken together, is something remarkable. Above and below our solar system sit the control systems of our sun's activity, the cleanest astronomical observing platforms in our neighborhood, and the unexplored geometry of the very shield that makes complex life on Earth possible. Everything we most need to understand about the environment of our solar system is concentrated in the one direction we have found hardest to reach. It is as if the most important rooms in a building are all on the roof, and no one has yet built the stairs. The missions being discussed now are serious. Solar Polar Imager, a proposed NASA concept, would use a combination of solar sail propulsion and gravity assists to tilt a spacecraft into a true polar orbit of the Sun within roughly 6 years. The sail would use the pressure of sunlight itself, pushing on a vast metallic sheet kilometers across to gradually walk the spacecraft's inclination higher and higher over successive orbits. No fuel, just photons, slow, patient, and persistent. Other concepts combine a sail approach with what is called the solar Oberth maneuver, a tactic where the spacecraft first drops toward the Sun to build extreme speed, then fires its engines at the closest possible point to the solar surface, where the efficiency of a rocket burn is at its mathematical maximum. The energy return from burning at perihelion is enormous compared to burning anywhere else. The fall becomes the launch. These missions have not yet been built. The funding cycles are long and the engineering challenges are real, but the scientific community's understanding of what is waiting up there, now sharpened by Solar Orbiter's early glimpses, has made the motivation undeniable. The polar regions of the Sun are not a curiosity at the edge of the scientific agenda. They are one of the central unanswered questions in heliophysics, space weather prediction, and our understanding of how stars behave. Consider what it would mean to finally see it. A spacecraft rises above the ecliptic. The dust of the plane drops away. The zodiacal glow disappears. And ahead, the north pole of the sun becomes visible from directly above for the first time. Its coronal holes open like dark eyes, its magnetic field lines threading outward into space in a geometry no photograph has ever captured. Surrounding all of it, curving away in both directions below, is the thin, flat disk of the solar system, lit softly by scattered sunlight, with 8 planets tracing their ancient circles in a plane so flat it barely deserves the word. And beyond the disk, the heliosphere wraps around everything in whatever true shape it actually holds, finally visible from the right angle to tell us which model was right. That image does not yet exist. No camera has ever taken it. Of all the extraordinary photographs humanity has produced in the space age, of storm systems on Jupiter, of the surface of a comet, of Pluto's frozen mountains, of Earth rising over the lunar horizon, the single image that would change our understanding of where we live the most is still waiting. It is the photograph looking down at our own solar system from directly above its star. We know what it would show. We know what it would teach us. We simply have not yet built the machine to go and take it. That photograph is coming. The only question left, the one that should sit quietly in the back of your mind long after this video ends, is this. When the first spacecraft finally climbs directly above our sun and sends that image back, what will it feel like to see your entire solar system for the first time? All of it, every planet, every orbit, every story of exploration, compressed into a single, thin disk hanging in the dark below you. What does it mean to finally know where you live? Tell us in the comments. Because that photograph may arrive within your lifetime. And when it does, it will be the most important image the human species has ever taken.